Hello everyone and welcome back to Algebra 1-2, where we look at topics in Algebra 1, Algebra 2 and additional mathematics. Indices play a very important role in our understanding of algebra and how algebraic terms relate to each other, especially when we're multiplying or dividing those terms. And so it is very important that we spend some time to look at algebraic terms through the eyes of indices and see how we can use those indices or index laws to evaluate numerical operations and also how to use them to simplify algebraic expressions. That will be our task for today, to refresh ourselves on how to use the indices rules, and if we haven't learned them before, then to learn them now and get a good understanding of how to use them when we are simplifying algebraic terms. Now, look at this algebraic term right here. We have three parts. We have here a coefficient. So this is your coefficient, the 5. It multiplies the x to the 4. The x to the 4 in this instance, we're going to call it our base. And here we're going to call this our power. Sometimes we call it an exponent. Sometimes we call it an index. So this term is made up of the coefficient, the base, and the power here. And the power here or exponent tells you how many times you write out this base when you're trying to multiply. So x to the 4th here would simply mean x times x times x times x. So we'd write it out 4 times for multiplication. All right, so let's look at the first rule. And the first rule is the law of multiplication. So when we're multiplying similar bases, the rule simply says that we add the powers. So if we are multiplying similar bases, notice that these two bases are the same, then all that we need to do is to add these powers. Now let's write down something and look at it real quick. Let's say we start by writing down 2 to the 3rd times 2 squared. Now, what does this mean when we write it out? Now, 2 to the 3rd means we're going to write 2 times 2 times 2, and we're going to multiply that by another 2 times 2. So here we have it, 1, 2, 3, 4, 5. So 3 times for this one and 2 times for this one. Let's show it there. So 2 to the 3rd times 2 squared. And if you look at it, you realize that this 2 is being repeated 1, 2, 3, 4, 5 times. And that's exactly the idea behind multiplying similar bases, that if you have this kind of situation, 2 to the 3rd times 2 squared, then you do not need to go through the problem of writing it out. Once the bases are the same, then all that you need to do is to add the powers. So we end up with 2 to the 3 plus 2, and that gives us 2 to the 5th power. And that's your answer. If you are multiplying, for example, 3x, let's use a different letter here. Let's say we want to multiply 3y squared, call this 1, call this 2, 3y squared times 2y to the 7th, for argument's sake. Then notice now that we have coefficients, and when you're multiplying this thing out, you need to deal with your coefficients differently. So we're going to multiply 3 times 2. Those are our coefficients, and our base here is y. Notice it's the same base, so we write our y, and then we simply add the powers, and notice that the bases are the same, so we can simply go ahead and add 2 plus 7, and so our answer here would be 3 to 6. So we have 6y to the 9th power, and that would be your answer there. Notice the rule says when you're multiplying similar bases. So if you're multiplying similar bases, here we are multiplying, here we are multiplying. So if you have something like a to the 7th plus a to the 9th, this cannot be, this multiplication law cannot apply to this. Simple reason is that the rule says when you are multiplying similar bases, and notice that in the middle here we do not have a multiplication, we have a plus sign, so we cannot use the indices law in this situation. The indices law applies when you are multiplying similar bases. All right, let's move on and look at the law of division. Now, in the same sense, let's write down 2 to the 5, and we're going to divide that by 2 to the 3rd. Now let's write this out by saying 2 to the 5, write it in fraction form, in rational form. 2 to the 5 divided by 2 to the third, and let's write it out. So 2 to the 5 would mean 2 times 2 times 2 times 2 times 2. That's 1, 2, 3, 4, 5 times. Very good. And we're dividing that by 2 times 2 times 2. Now what happens when we're dividing is that this will divide this out. This will divide this out, and that divides that out. And what we're left with is 2 times 2. And writing that in index form will give us 2 square. So the idea then is that we do not have to go through all of this when we're using similar bases. Notice that the bases are similar. So because the bases are similar, we can simply say 2 to the 5 divided by 2 to the third is going to be equal to 2 to the 5 minus 3, and that gives us 2 square. Of course, you could write down the value of 2 square, which is 4. But the idea is when you're dividing similar bases, then we subtract the powers, or we subtract the exponents. Here we have another case. Let's look at this one. Suppose we want to divide 5 square divided by 5 square. It says any base, except 0, of course, raised to the 0 power is equal to 1. Now 5 square divided by 5 square, we know what 5 square is. 5 square is 25. Or we can write it as 5 square. Let's write it out here. 5 square divided by 5 square, which gives us 5 times 5 divided by 5 times 5. And that gives us 25 divided by 25. And that, of course, is 1. So it would seem then that if we are going to use the division rule, and 5 square divided by 5 square is going to give us 1 here. But if we write it out using the approach we did here, we're going to get 5 square divided by 5 square is going to be equal to 5 to the 2 minus 2, which gives us 5 to the 0. And 5 to the 0, naturally, because we had worked it out before, we get an understanding of what this 0 power means. And this 0 power is telling us here that this 5 raised to the 0 power is 1. And for that matter, any number that you can raise, any number except 0 that you raise to a 0 power, anything for that matter that you raise to a 0 power, gives you 1 as long as it is not 0. 0 to the 0 has no meaning in mathematics. So when we write 0 to the 0, this has absolutely no meaning. It's one of those things that we say it's undefined. There's no answer for it. It just doesn't compute. But any other number or any other letter, as long as it is not 0 and you raise it to a 0 power, that answer is 1. Getting back to this though, when you're using the division rule, as long as your bases are the same and you're dividing, you can just go ahead and subtract the powers. All right, let's move on. Now let's look at when we're writing out powers and products and quotients. So when we're using the multiplication rule, we can say, all right, 2, let's change about this ink. We can say 2 to the third times 2 to the 7th would give us 2 to the 7 plus 3. And that would give us 2 to the 10th. What if we have instead 2 to the third times or 2y squared? Let's use that. 2y squared raised to the third. How do we deal with this? And this now is a product because we have 2 times y squared. The rule is telling us that we can simply apply the idea the same way. So if we are raising a power to another power, notice that this 2 is being raised to the third power here, and this y squared is being raised to the same third power here. Then what we can simply do is to bring everything to that power outside. So to raise a power to another power, we simply write down the base and multiply the powers. So here we have, this is going to be raised to the second power. The power here is 1, and 1 times 3. And then y and 2 times 3. So it would give us an answer of 2 to the third, y to the 6th. And we can further simplify that because 2 to the third is 8. So it would give us 8y to the 6th. Now, in terms of You could apply this also to, for example, x to the 7th, y to this 2, and you're raising that to the 5th power for argument's sake, then it's x to the 5 times 7, and y to the 2 times 5, which is y to the 10, for argument's sake. When it comes to quotients, the same thing applies. So, for example, if you have 1 over 2, and you're raising that to the third, then it's 1 to the third power over 2 to the third power, and that would give you 1 over 2 times 2 times 2, which is 8 for argument's sake. And if it's letters, it's the same idea. If you have x to the square divided by y to the third, and you're raising that to the second power, then it's x to the 2 times 2, which is x to the fourth, over y to the 2 times 3 to the 6. So the same idea applies to products, as in this case. It applies to quotients, as in this case, and it's simply an extension of this law, just that you have something else in the bracket. If you put this here and put something else in the bracket, then it becomes, the multiplication law becomes the power or product rule. Apply the same thing to quotients as well. Let's look at another one. If we're looking at negative powers now, so negative powers is going to bring us a little bit back to the division rule. Let's divide a little bit. Let us say we're going to divide 2 square divided by 2 to the 5th power, and we're going to write it out using rationals. So we're going to write it as 2 square divided by 2 to the 5th power. Writing this out is going to give us 2 times 2 divided by 2 times 2 times 2 times 2, 1, 2, 3, 4 times 2. And when you try to divide that out, you realize that this divides this, and this divides this, and of course 2 into 2 is 1, and 2 into 2 is 1. So what we're left with at the top is 1 times 1, which is 1. And what we have here in the denominator is 2 times 2 times 2, which is 2 to the third when you write it in index form. And so what this is saying is, using the division rule, 2 to the 5, other way around, 2 square divided by 2 to the 5 would mean 2 to the 2 take away 5. Notice it's the same base. So we subtract the powers, and that would give us 2 to the negative 3. And what this is telling us is that 2 to the negative 3 is equal to 1 over 2 to the third power. So 2 to the negative 3 is equal to 1 over 2 to the third. And that's what a negative power means when we see them. So conversely, if we have, or rather, if we have 5 to the minus 7, we can always write it as 1 over 5 to the 7. And if we have a to the minus 2, we can always write it as 1 over a square. And if for argument's sake you want to write it the other way, so you say you have 1 over a to the third, you can always write it as a to the minus 3. So this is what the idea of a negative power means. A negative power does not mean a negative number. It simply means that you can write that number in rational form. So 2 to the second power divided by 2 to the 5th power gives us 1 over 2 to the third. And we can apply that by saying that we simply subtract the powers using the division rule. And what we find is that 2 to the third minus 3 here is the same thing as 1 over 2 to the 3. And we can rewrite this as 1 over 2 to the 3 is the same thing as 2 to the minus 3. Depending on what you want to do with it, or depending on the question, you can write them either way. A negative power in fraction form, or 1 in fraction form, you can write it back with a negative power. Next, we want to look at fractional powers. So what when you have a fractional power? Let's start by looking at this question here, 4 to the half. What would 4 to the half mean? What would it mean in terms of a power? Now, let's go back a little bit to the multiplication rule and say to ourselves, what if we have 4 to the half multiplied by 4 to the half? Then according to the multiplication rule, if we are multiplying similar bases, which these are, then 4 to the half times 4 to the half would mean 4 to the half plus half, which would give us 4 to the half plus half is 1, and 4 to the 1 is just 4. This is interesting and very important for us to notice. So if we multiply 4 to the half by 4 to the half, it gives us 4. Now, 4 to the half, what numbers can we multiply to get 4? Notice that 4 to the half is representing a number, and we are repeating it in multiplication. What other number behaves like that to give us 4? You'll remember that 2 times 2 gives you 4. And so what this must be saying is 4 is the same thing as 4 to the half is the same thing as 2. 4 to the half is the same thing as 2, and 2 times 2 gives you 4. And so what we find then is that when we have a fractional power such as a half, then 4 to the half power is actually saying this to us. It's actually saying square root of 4. And of course, you know that the square root of 4 here would be plus or minus 2. In this case, I'm just going to write down 2. So when we have a fractional power such as that, it's actually telling us to find a root. Now, 9, for example, to the 1/3 would be telling us to find the cube root. The cube root of 9. So let's write our 9, and then we write the 3. And whatever it is, so a to the 1 over m is going to be telling us to find the mth root, whatever that number is, the mth root of a. And you can always use a calculator to work these out. If you do not know them off the top of your head, you can always plug these in a calculator and work them out, in a scientific calculator for that matter. So a fractional power tells us that we must find a root. Notice that this has another number at the top. So it doesn't have to be 1. I'm just saying here that 4 to the half. Half means 1, means rather square root. 1/3 means a cube root. If it was, for example, 4 to the 1 over 5, then we'd be finding the 5th root of 4 for argument's sake, and it goes on and on and on. Now, when we're dealing with other numbers there, for example, 27 to the 2/3. Now, the 3 here tells us that we must find the cube root of 27. And how do cube roots work? Just as though you have 2 times 2 gives you 4, so we can say the square root of 4 gives you 2. Then, for example, 3 times 3 times 3 gives us 27, and we can reverse that and say, what is the cube root of 27? And the cube root of 27 goes back to being that number there, 3. So if we are trying to evaluate, for example, 27 to the 2/3, what it says here is that we are to take the nth root. So we are to take let's write it down here, 27 to the 2/3 means that we're going to take, for example, the cube root of 27, and of course you can do this on your calculator, the cube root of 27, and when you get the answer, you raise it to the top number. So here, the cube root of 27, remember, the cube root of 27 is 3, and so we're going to write that 3, because that's what this works out to, and we're going to raise it to that power there. And it ends up being 3 squared, which is 3 times 3, which is 9. So these things are actually very, very nice to use. Of course, if you're working with letters, x to the 2/3 times x to the 2/3, then you're not required to work out anything like this. You simply go ahead and use the multiplication rule or division rule or whatever rule applies to what you're doing with. And in this case, since we're multiplying, it's going to be x to the 2/3 plus 2/3, because we're not being required to calculate a value. So it's simply going to be x raised to the 4/3. 2 plus 2, 4/3. So here, when we have a fractional power there, and the number is not 1, we go ahead still and we find that nth root, whatever that number is, we find the nth root, and once we find it, we raise it to the power that's in the numerator. So it's the nth root raised to the m power. Now that we have talked about the multiplication rule, the division rule, powers and products and quotients, we can now use some of those tools to simplify some expressions. So let's do that. Here we have 3 questions. 1, 2, 3. And we want to use the index rules to go through and simplify these, because that is where we often come across using indices other than doing it by itself. We want to expand brackets, for example, and so we want to know what the powers are. So here we have x to the third times this bracket. And so what we're going to have is here, we're multiplying this using the distributive law. X to the third times x squared would give us x to the third times, I'm going to use a dot, and plus x to the third times x to the fourth. And so we have here now x to the third times x to the fourth, same base, so we can simply add the powers there. So it gives us x to the fifth power plus x to the third times x to the fourth. We go ahead and we add those. 4 plus 3 gives us x to the seventh power. And we stop here. Notice that we cannot reduce this any further because this is now saying x to the fifth power plus x to the seventh power. They're the same base, but this is a plus sign, and we cannot, in algebra, add unlike terms together into one term. So we'd have to leave this as is. That is our answer right there. In this question, we're required to do a multiplication, then division. So we have t to the third times t to the sixth. Using the multiplication rule, we can say t, let me use a different ink for this one. We can say t raised to the 3 plus 6 divided by t to the fourth, which gives us t raised to the ninth. 6 plus 3 is 9, divided by t to the fourth. And remember, this is division. And the division law says when you're dividing similar bases such as this, you simply go ahead and subtract the powers. So what we're going to have is t to the ninth minus 4. And the 9 minus 4 here gives us t to the fifth power. And that is our answer there. Here's one that is a little more interesting. So here we have w squared times w to the negative 3 divided by w to the negative 4. So at the top in the numerator, we're going to multiply. So we're going to go ahead and add our powers. So it's w raised to the square times this, which is w to the 2 plus negative 3. And then we're going to divide that by w to the negative 4. Now when we add 2 plus negative 3 here, we get w to the negative 1. And we are dividing that by w to the negative 4. Now that we have completed the numerator, this is now a division. So it's saying w to the negative 1 divided by w to the negative 4. Remember, when you are dividing similar bases, you go ahead and subtract the powers. So what we're going to have here is w to the negative 1 minus negative 4. And that is going to result in w to the minus 1 plus 4. Which gives us, for our answer, w to the third. So we can use indices to simplify algebraic expressions. We can use them to simplify numeric expressions. And especially when you're simplifying numeric expressions, you probably want to pay attention to your calculator because your calculator has a button. Sometimes on your calculator, it looks like this, a little up arrow that indicates powers. Sometimes it's x to the y, or sometimes it's written the other way around, y to the x. And so these buttons on your calculator will allow you to work with stuff, especially when they're numbers, like you want to find a half raised to the 2/3. You can simply use these buttons to find it. And so now that you remember, now that you have seen how indices work, it is important that you get some practice in to cement these skills. And of course, if you haven't subscribed to our channel yet, then please do so. We appreciate your support. Thank you for watching, and we'll see you next time.